Hey class, this is the beginning 48 and 50 of problems 19b. So let's take a quick look. Here we're calculating delta S standard values for the following reactions by using the tabulated entropy values from Appendix C. I have Appendix C has been scanned and attached to this homework assignment, so you should be able to open that on your iPad, I'm hoping. And in each case, explain the sign of delta S. Now remember, if it's a positive delta S, it is a irreversible. If it's negative delta S, it's reversible. I think it's something like that. I'll check to make sure. Okay, so let's talk about how do we find this information here. Let me just check to make sure that this looks like this, we're in good shape. There we go. Okay. So here I have N2H4, H2, and 2NH3. So like I do with all of my stuff, I'm going to do the products always seem to come first, minus these ugly backwards S's are called summation signs. And what that means is I'm going to take my products first, so this is the one I'm going to look up first. The 2 does matter, so it's going to be 2 times. So whatever my products are, it's going to be 2 times whatever that value is. That's just ugly. There we go. For NH3, that's going to be here. And then whatever I get from that, I'm going to subtract from, and then these two, the N2H4, subtract from the H2. These are going to be added, of course, and then the whole thing's going to be subtracted. So here's what this looks like. So I actually have a picture of the scans. So let me do some highlighting so you can get the C. First of all, H2 does have an S value. We'll come back to that. That's 130.58. And then over here, I have nitrogen with NH4, and that is going to be 238.5. And then where's the NH3? And I believe the NH3 is a gas, which means I have 192.5. Okay, so 192.5, that's the important point for this one right here. I'm going to flip back and forth. 192.5 multiplied by 2 equals a certain amount. The N2H4 is 238. Where are we at here? 238.5 positive. These are all positives. 238.5. And then the H2 is this one right here, and that's 130.58. Okay, these are all joules, I believe. Let's take a quick look to see what it is. This is in joules mole per Kelvin. Okay, that makes a difference, especially when we use S in a different equation. So all I'm doing here is adding these two together. I'm going to multiply times 2 to get a certain amount and divide. Where's my calculator at? So you can see how this works. These all work exactly the same way. There's no difference. You're going to start with the products. 2 times 192.5 equals 385, and we're going to subtract, and then I put these two together, 238.5 plus 130.58 means 369.08. So when I subtract these two, like this, I get 385 minus 369.08 equals 15.92. That is a positive. That does make a difference. And that is kilojoules per mole Kelvin. Like that. Kilojoules per, joules per mole Kelvin. Bonehead. Joules per mole. Oops. Oh my God. Okay, you know what I mean. Kelvin. There. Holy cow. So make sure that when you're doing this, that you're taking the products, AlCl3, 3 times whatever you get for that, like that, minus, and then you're going to put 2 times, this is for Al, plus 3 times, this is for Cl2, like that. Add those all together, and then you take whatever you get here minus here, and what that equals then. Okay, so follow my procedure for A, and you should be able to get all of these exactly the same way. I got, ooh, that's not a 2, that's a 3. I'm sorry. I don't mean to confuse you. This would be a 2 times this, because there is a 2 in front of the AlCl3. There's a 2 in front of the Al, and there's a 3 in front of the Cl2. So I made a mistake there, so go back and change that. So now the coefficients look correct, and then the values, you get the values from Appendix C, and you put them in here, here, and here, and then just do the math equation. Okay, let's take a look at 50. So for 50, it says, what's the meaning of the standard free energy change as compared with, so what's the difference between the delta G standard with that and the delta G without the standard? Okay, so this part here means for any temperature. Now, as it turns out, there's a term that is negative T delta S, and this T right here, of course, means temperature. So at the standard, let me see if I can get there we go. At the standard here, this standard means at 25 degrees Celsius, and it's what we have all of our Appendix C information in. So oftentimes we will talk about the delta G standard because it's a common temperature, and we have information on the formation of different compounds at that temperature. So this part right here, if you remember, I'm pretty sure I talked about this already, the delta H minus T delta S. It's this part right here that makes the difference between not having the degree sign over here and having the degree sign over here. And this one is at 25 degrees Celsius. So that's what we're talking about. Any process that occurs at a constant temperature and pressure, what's the significance of delta G at 0? There's one significance. When delta G is at 0, I don't even know what I'm spelling anymore. Then it's at equilibrium. Our reaction is at equilibrium, and that's what that means. For any process that occurs at constant temperature and pressure, what's the significance of delta G at 0? For a certain process, delta G is large and negative. Does this mean that the process necessarily occurs rapidly? Okay, here's something. Delta H is our enthalpy term, minus T delta S is our entropy term. Under none of these terms does anything discuss rate of reaction. Okay, so the rate of the reaction is still unknown. If a delta G is negative, that means it happens spontaneously, but it does not mean it happens quickly. Even if it's a huge delta G negative, like a very large delta G, still doesn't mean that it happens quickly. It just means that it happens very spontaneously. Okay, now so delta G does not make a reference to the rate of reaction. We still don't know what the rate of the reaction is for delta G. So it says, does this mean that the process necessarily occurs rapidly? And the answer, of course, is no. All right, thanks for paying attention. Stay tuned for part B.